Okay guys, let's take a look at Alternating Series Day 1. This is our 8th test that we will be learning, and let's take a look at it. Alright, here's some examples of alternating series. We actually have encountered them before. This is the piece right here that causes the series to alternate. And over here is kind of a definition. Basically, an alternating series is a series whose terms are alternately positive and negative. And typically with regular series, non-alternating series, knowing that the limit goes to 0 really isn't that much help. But on an alternating series, it is actually part of the test to determine whether the limit goes to 0. We have a couple of things that have to be true in order to use the alternating series test. First of all, I need to point out this a sub n. I need you to notice the way this is written. A sub n is the non-alternating part. It's not the alternating part. So when it asks you to do things with a sub n, like here, take the limit of a sub n, go into infinity, it's asking you to do just the non-alternating part. In both cases, it's written separate from the alternating part. Even if on your paper it's not written separate, that's what it means. We need to take it separately. So that's the first thing that usually really troubles students. We just really be sure we need to understand what they mean by a sub n. And first of all, that has to be greater than 0. Those terms need to be positive. And here are the two conditions. So it's the alternating series test. What it tells us is that the alternating series will converge if these two things happen. Number one, the limit of the nth term part goes to 0. That's the first thing. The second thing is, and this is written kind of in mathematical notation, what this means is that, and notice that it's just the nth term part they're talking about here. That's not the alternating part. With the nth term part, the next term, a to the n plus 1, is the next term, needs to be smaller than the previous one, which is a very fancy way of saying that they need to decrease in magnitude. You know, magnitude being we're not paying attention to the alternating part, we're paying attention to the absolute value. So, in other words, here's our test. A alternating series converges if, first of all, we have an alternating series. They alternate in signs. Second of all, the terms decrease in magnitude. And the third criteria is that our a sub n needs to have a limit of 0. This piece right here. Okay? So this note is down here just as a caution. The alternating series test will only prove convergence. It does not prove divergence. So to prove the divergence, we actually have to go to a different test. Okay? We actually have to go to a different test. So the nth term for convergence there, I figured out how to do it. I was like, oh no. I've never stopped it in the middle before. It's probably ruined now. Alright, I think it's recording. We will have to check. Okay, so we can only use this test to prove convergence. We can't use it to prove divergence. So if if we don't have a limit of 0, what we'd want to do is we want to switch over to the nth term test for divergence. That was like the first one that we learned, which tells us that if we take the limit to infinity and it's not 0, that the series diverges. So that's just a note down here. So here we go. And there's one, oh no, there was something else. Oh, there's another note that I need to make sure. This right here, decreasing in magnitude, probably 90% of the time. 90% of the time you're going to be able to tell that the series is decreasing in magnitude by just looking at it or writing out a few terms. Sometimes, around 10% of the time, it's going to be too difficult to do that. And so there is a way that we can show that it's decreasing, and I'm just going to write that. It, again, only happens about 10% of the time. What we would do is we would take the ratio of the next term over the previous term. So we're going to look at, so if it is difficult to tell that we're decreasing, what we want to do is we want to use this ratio, the a sub n plus 1 over a sub n. And we work that ratio out, simplify it. If that ratio turns out to be less than 1, then it's decreasing. Okay, that is a way that we can kind of get around the fact if they're really difficult. And I don't have one on these notes, but I do have one on the daily work that you would need to do this a sub n plus 1 over a sub n and test when we would test that. Okay? So, let's work on our first example. We want to determine whether the following series converges or diverges. Okay? Now, the first thing is, let's kind of circle this part. This is our a sub n part. That's the part that we're going to be dealing with for our limit, decreasing in magnitude. So let's take a look at it. All right, is this alternating? So we're going to check the alternating. So our first criteria is, does it alternate in sign? And yes, this part right here causes it to alternate in sign. Does it decrease in magnitude? Well, let's kind of look at it. Let's see if we can tell by looking. If I put a 1 in here, I get 1 over, 1? If I put a 2 in here, I get 2 over 3. Okay, that's definitely less than 1. If I put a 3 in here, I get 3 over, what is that going to give me? 6, 5, 3/5. So it looks like it is decreasing. We're going to say it's decreasing in magnitude. Okay. Our third test is to take the limit. The limit as n goes to infinity of n over 2n minus 1. Okay, so we look at that and we get a half. Oh, that's not 0. So this alternating series diverges, right? But it doesn't diverge by the alternating series test. It diverges by the nth term test. So we say diverges by the nth term test. Now let's talk about this for just a moment. When we approached the nth term test and we had an alternating series, we split it. If you remember, we split it into odd terms and even terms. Remember that? Where we'd have the positive terms and the negative terms. That is the technical way, the correct way to do this. Let's look at, but I've seen lots of mathematicians write it this way. So I think we're okay with this. Let's talk about why. This is the positive terms. This is either the odd or the even. Let's see which one. If I put a 1 in there, what does that give me? That gives me an even. That gives me positives, right? So this is the odd terms. The odd terms go to 1/2. What would happen with the even terms? Where do you think they're going to go? To negative 1/2. And basically, both of those numbers aren't 0, right? And even if this one, what would happen if the other set of terms went to 0? Would that make this converge? No, because half of them don't go to 0. Are you with me? So a lot of mathematicians will just go here, and since for the nth term, they'll just work this limit on the nth term instead of both positive and negative, and will use the nth term test to prove divergence. Okay, so that's okay if you don't want to split it off into even and odd terms. But it's pretty easy to do the other one. So this would be our odd terms. Our even terms would be the negative version of this. And that would give me negative 1/2, which also is not 0. So we still diverge by the nth term test. Okay, so what I'm telling you is you can use this and say diverge by the nth term test, or you can go ahead and write out the even and the odd terms and come up with the same result. Either one of those will be fine with me. Okay? All right, so that diverges. All right, let's go to our, are we okay? Ready? Questions? Okay, let's go to the next slide. All right, so a couple of examples. We want to determine whether the following series converge or diverge. So let's do that. All right, here's the nth a sub n part, and you don't have to circle that. I'm just kind of making sure we really understand what we're doing here. And our first question is, does this series alternate? Go positive, negative, or vice versa? And it does. So it alternates. Is this decreasing? N over ln 2n. Now that's a little bit harder to tell. So before I go to that extent to try to figure out whether that's decreasing or not, let's look at the limit going to infinity first. If the limit isn't 0, there's no sense in us spending time trying to figure out if this is decreasing in magnitude. If I take the limit of this, the limit as n approaches infinity of n over ln of to 2n, ln of 2n, what is that limit going to tend to? Infinity. What are we using for that? I'm hoping we remember that. What are we using? The rates of growth, right? The rates of growth, remember that? We're using rates of growth to determine this. This algebraic piece, the numerator, is going to grow faster than the natural log piece. That's on your yellow sheet if you don't remember the order of the rates of growth. And so since the faster growing one is on top, this is going to tend to infinity. So even if this was decreasing in magnitude, that's not going to help us, is it? Because the limit is infinity. Now, that means that this alternating series diverges, right? But, so that's not 0. So that diverges, but what is the alternating series diverging by? By the nth term test. This diverges by the nth term test. Okay? Part C, let's look at this one. All right, so it's alternating. Yes. Is this one the a sub n term, which is just basically 1 over n? Is that part decreasing in magnitude? Yes, as we get larger and larger, we're decreasing in magnitude. Let's see, the last thing is the limit. So the limit as n goes to infinity of 1 over n, this tends to 0. So that checks out. So therefore, this series converges by the alternating series test. Okay, so it converges by alternating series test. Okay. The only other concept we're going to be looking at today is absolute and conditional convergence. All right. Before we get there, let's just look. They're fascinated with the harmonic series, and we also have an alternating harmonic series. Now, the regular harmonic series, does that one converge or diverge? It diverges, doesn't it? That's a p series where a p of 1. The alternating harmonic series actually is this. What did it do? It converged. This is just like a picture of what it would look like. They drew a little picture. It's getting closer and closer to the sum, which is kind of weird that the alternating series for this, the alternating harmonic series converges, but the actual harmonic series diverges. That's what conditionally convergent means. When we're dealing with these two words, conditionally convergent and absolutely convergent, what we're trying to decide is, will the series converge if it's alternating or if it's the absolute value? In other words, if it's always positive. We're going to look at both of those. And this tends to confuse students, so I'm going to kind of back up here. What we do is we deal with the alternating series first. Okay? We find out if the alternating series converges. We do that first, just like right here. Right here we did the alternating series and we determined that it converges. All right? The second step, and I'm just going to use this part C as a demonstration of what these words mean. The second step would be to do the absolute value. So I would take this series and I would do the absolute value of it. Okay, I would determine whether that converges or not. Now, how can I write this absolute value? Rewrite it. Right, just 1 over n, right? So this is the same thing as that. The absolute value of this alternating series is the same thing as that. And we know that that is a p series, right? P is 1. And by p series, does this converge or diverge? It diverges. So since the alternating series converges and the absolute value of the alternating series diverges, this particular series is called conditionally convergent. This would be conditionally convergent. Now, if the absolute value of the series converged, then it would be absolutely convergent. And if the alternating series diverges, you're pretty much done. If the alternating series diverges, it diverges, you're done. There is no absolute or conditional convergence. That's why we start with the alternating series. We start with it and we decide what happens to it. Does it converge or diverge? If it diverged, we're done. Everything diverges, period. If it converges, then we check the absolute value of that series out and see whether it converges or diverges. If it converges, then we're absolutely convergent. If it diverges, then we're conditionally convergent. Okay? Is that okay? All right, so let's check this one out. We're going to check the alternating series part of this one out first. So, does it alternate? Yes. Is this the a sub n part? That's this part, like there'd be a 1 there. Is this part decreasing in magnitude? Yes. We decrease in magnitude. Check. All right, let's do the limit. The limit as n goes to infinity of 1 over square root of n. What does this limit tend to? 0. So therefore, this converges by the alternating series test. Okay, now we have to check the absolute value of that series. All right, so let's do that. So we're going to check the absolute value of this guy. Now I can rewrite him, right? I can rewrite him without the alternating part. So n equals 1 to infinity, 1 over square root of n. What kind of series is that? That's a p series. And my p value is what? 1/2. So by the p series, does this converge or diverge? This is smaller than 1, therefore it diverges by the p series. So, is this series, this original series, is it conditionally convergent or absolutely convergent? It's conditionally convergent because its absolute value partner diverges. So therefore, this one is conditionally convergent. Okay? Is that okay? All right.